right, everyone. Ready to jump into something kind of cool? Like,
Yeah.
ever wonder how a C program actually gets the computer to, do things?
Yeah, it's kind of like magic.
We're going to break down the whole process here.
Uh-huh.
From, like, the second you hit save on that .c file all the way to the CPU actually running your code.
It's a wild ride.
So think of it this way. You've got this, well, human-readable code, right?
Right.
But the computer at the end of the day only speaks in, like zeros and ones.
Mm-hmm.
So how do we bridge that gap? That's what this whole deep dive is all about.
Yeah, that's the core of it, isn't it?
It's not like a single jump from code to execution,
No. It's really more like a series of steps. Each step has, specialized tools that handle the process.
Okay, so to make this a bit more real, let's say you wrote a simple program in C, just to add two numbers together, right? We're going to follow that program's journey as it goes through all these stages, kind of like seeing how the sausage is made.
I like that. I like that analogy.
So are you ready to dive in?
Absolutely. So let's break down those stages. The first one is preprocessing, and it's handled by you guessed it, the preprocessor.
All right, so the preprocessor, that's our first character in this story. What exactly does it do?
Well, you can kind of think of it like the code's assistant, like a little helper.
Mm-hmm.
It goes through your code looking for specific instructions. We call them directives. And those always start with a hash symbol, the hashtag.
Ah, okay, so like hashtag includes stdio.h, that thing we use all the time.
Exactly. That's a perfect example. So when that preprocessor sees hashtag include, it's like a signal. It knows, okay, I got to grab the content from that file. In this case, it's the standard input-output library, and basically paste it right into your code.
So it's kind of like behind-the-scenes setup then, getting everything ready for the main event.
Exactly. You got it. It's preparing that code for the next big stage. And this is where things get really interesting. It's called compilation. This is where we take that language we understand and turn it into something closer to what the CPU can actually work with.
Okay, so time for the compiler to take the stage, right? What happens in this whole translation process?
So the compiler is like our master code interpreter. It takes your C code and converts it into, well, we call it assembly language. Assembly language is a low-level language, meaning it's much closer to the actual hardware itself. And it uses these mnemonics, which are like symbolic representations of machine instructions.
Okay, so it's still human readable, but it's getting closer to the machine's language then.
Yeah, exactly. But the compiler is doing even more than just translation. It's also like a super strict teacher, right? Checking your work for any little mistake. It makes sure that you're using the right data types, that your variables are all declared correctly, all according to the rules of C.
So it's like enforcing the law of the land,
Yeah.
making sure our code is, well, behaving itself.
Uh-huh. Yes, exactly. It can even try to optimize your code, like make it run faster or use less memory. The compiler, it really is a workhorse in all this. And then what it spits out is an assembly language file, all ready for the next stage in our journey.
All right, so we went from C code to assembly language. We're getting closer to that machine code now. What's next?
Next up, we've got the assembler. And it takes that assembly language file that the compiler just made, and the assembler converts it into machine code. And this is the language that the CPU understands. It's a whole bunch of zeros and ones.
Ah, okay, so if the compiler is the translator, then the assembler is like the encoder, right? It takes those mnemonics and turns them into that raw binary that the CPU actually wants.
That's a great way to put it. Yeah, you got it. Each assembly instruction usually has like a direct corresponding machine code instruction, and what the assembler produces is an object file.
Okay, so we've got this object file. Is that our final executable program?
Not quite yet. We're almost there, but there's a bit more to do. You see, most programs, even simple ones, they use functions from libraries, right?
Mm-hmm.
Like if you want to display something on the screen, you use printfy, which is part of that standard input-output library we talked about. But that code, it actually lives in a separate object file.
Oh, so we need to bring all those pieces together somehow.
Exactly, and that's where our next variant comes in, the linker. It's like a master chef, right? Taking ingredients from different places and making them into a final dish. The linker takes your object file, combines it with any other object files from those libraries, and then it resolves all the references. It makes sure all the pieces are connected correctly.
Okay, I think I get it. So like when our code calls that print function, the linker makes sure it knows where to actually find the code for that function.
Exactly, like fitting puzzle pieces together.
Right. And the output of all this is our executable file. Finally, that's the program we can actually run. But wait, there's still another step before we get to run it?
One more. This last step is called loading. And this is where the operating system steps in. It takes our executable file and loads it into memory. specifically RAM. RAM is like the computer's workspace, where the program can actually live and operate.
Ah, okay. So it's like setting up the stage for the performance, making sure there's room for the code, the data, all the storage the program needs.
Exactly, exactly. And once the loader's done its thing, the stage is set. And then the star of the show can finally take over the CPU.
Right, the CPU, that's the brain of the computer.
Yeah.
Now we get to see all those instructions actually running. But I think that's a good place to stop for now. We've covered a lot of ground. We'll pick up the rest of this journey next time.
Yeah, that sounds good. We've laid a good foundation here for how a C program really comes to life. We'll delve even deeper into the CPU's role next time. Plus, we'll cover some other fascinating details. Until then, think about all those steps we've talked about and how they work together to turn your code into action.
It's a real team effort.
Welcome back. So last time, we left off with our C program loaded up in memory, ready for the CPU to take over.
Right, right. And we were talking about the compiler being this meticulous translator, right? Turning our C code into assembly. But I have a feeling there's more to that story, isn't there?
Yeah, there's definitely more to it. Like the compilation process itself, it's like a whole mini factory with these distinct stages. It's not just a straight-up one-to-one conversion.
Okay, I'm intrigued. Break it down for us. What are these stages within compilation?
Okay, so the first stage is called lexical analysis. Now, think of it this way. The compiler reads your code, like character by character, right? And then it groups those characters into meaningful units. We call those tokens.
Okay, so like if we have a line of code that says int count equals 10, the lexical analyzer, it would break that down into separate tokens, like int count, the equal sign 10, and the semicolon.
Exactly, you got it. It's kind of like identifying the individual words and punctuation in a sentence, you know.
Right.
And those tokens, they become like the building blocks for the next stage. That's syntax analysis.
Syntax analysis. That sounds like it's where the compiler starts checking to see if our code is actually following the rules of C.
Precisely. Syntax analysis, we also call it parsing sometimes, is all about making sure that the arrangement of those tokens, that it follows the grammatical rule, so to speak, of the C language. It's like checking to see if a sentence is grammatically correct.
Right, right. So if we forget a semicolon or mess up some parentheses, the syntax analyzer is going to, like, catch us red-handed.
You got it. The compiler is very, very strict about syntax, and often during this stage, it'll actually create a tree-like structure. We call it an abstract syntax tree, or AST for short.
Interesting. So it's not just checking for errors, it's also making like a representation of the code structure.
Exactly. That AST, it visually shows the relationships between all the different parts of your code, and this is super helpful for the next stage, semantic analysis.
Semantic analysis. Now that sounds deep. Is that where the compiler checks to see if our code actually makes logical sense?
You got it. You nailed it. Semantic analysis, it goes way beyond just syntax. It's all about the meaning. The compiler checks, like if you're using variables correctly, if the types are all compatible, if there's any kind of logical inconsistencies in your code.
So like if I try to add a string to an integer,
Right.
the semantic analyzer is going to be like, nope, not happening.
Exactly. It's making sure that your code is not just grammatically correct, but that it also semantically, makes sense. And then after semantic analysis, we get to a really cool stage. It's called optimization.
Optimization. Now that's something every programmer wants. What exactly does the compiler do during optimization?
So this is where the compiler really gets clever. It looks at the code and tries to figure out ways to make it better, but without actually changing what it does. So it might rearrange some instructions, or maybe eliminate some redundant code, or even just find more efficient ways to do certain operations.
It's like having a code coach going through your program and suggesting all these improvements.
That's a great way to think about it. And the compiler's goal here is to make your code run faster or use less memory, or ideally both. And this whole optimization stage, it's really key to why compiled languages like C are so efficient.
Okay, so we've gone through lexical analysis, then syntax analysis, then semantic analysis, and optimization. So what's the final output of all this? What does the compiler actually produce after all those stages?
Well, after all that, the compiler finally generates the assembly code, all ready to be passed on to the assembler.
Phew, that's quite a journey. But now we've got our assembly code, much closer to what the CPU wants to see. What happens next?
All right, so now the assembler takes over. Remember, we talked about it before. It takes that assembly code and converts it to machine code, those binary instructions that the CPU can actually understand.
Right, right. So it's like encoding those assembly mnemonics into zeros and ones the stuff that the CPU circuits can actually work with.
Exactly, you got it. Each assembly instruction usually has a pretty direct corresponding machine code instruction, and the assembler then produces an object file with this machine code in it.
Okay, so we got our object file.
Yeah.
We were talking about how most programs use functions from libraries, right?
Right.
How do those parts actually get, like, integrated into everything?
Right. That's where our friend the linker comes back in. He's got a lot of work to do. It combines our object file with those object files from the libraries, remember? And it also handles what we call resolving references. So when our code calls a function like print again, the program needs to know exactly where to find the code for that function. The linker takes care of that.
Right. It's like the linker's making all the connections, ensuring everything's wired up right.
Exactly. Precisely. And there's one more really crucial task the linker does. It's called relocation. See, when we compile those object files, the addresses for the code and the data, they're often relative, meaning they're not fixed yet.
Wait, why would the addresses be relative? I thought they should be, absolute, pointing to specific spots in memory.
Well, you see, when you're compiling an individual object file, you don't know exactly where in memory it's going to end up when the whole program actually runs. That's up to the operating system and what other programs might be running at the same time.
Okay, so those addresses need to be, adjusted once the program is actually loaded into memory.
Exactly. That's what the linker does during relocation. It modifies those addresses in the object files so they're correct for the final executable file. It's like, imagine everyone moves into a new neighborhood, all the street addresses have to be updated.
Right. Makes sense. It's all about making sure the program can find what it needs once it's up and running. So, okay, now we've got our executable file all linked together and ready to go. What's next?
All right, so now it's the operating system's turn to take center stage. Remember the loader? Well, that's part of the operating system. And its job is to take our shiny new executable file and load it into memory.
Right, the loader sets up the stage, makes sure there's room in RAM for the code, the data, any temporary storage the program might need.
Exactly. And once that program's loaded up in memory, the CPU can finally start executing those instructions.
Okay, so the CPU is like the star of the show. But it's not working all alone, right?
You're absolutely right. The CPU, it works closely with the operating system. Think of the operating system like the conductor of an orchestra, It's managing all the resources of the computer, the CPU, the memory, all the input-output devices, and so on.
Okay, so when our program needs to do something, like display text on the screen, it doesn't actually directly control the monitor's hardware.
Exactly. Instead, it makes a request to the operating system. And the operating system, it handles all the low-level details of actually talking to the hardware. For example, when you call that print function in your C code, it's basically sending a message to the operating system saying, hey, can you please display this text on the screen?
Okay. So the operating system acts as a go-between, right, between our program and the hardware. Takes care of all those nitty-gritty details.
That's a great way to put it. It keeps our C program from having to worry about all those complexities of actually talking directly to the hardware. It can just focus on the logic of the program itself. And the operating system handles all that messy, behind-the-scenes stuff.
That's a pretty awesome collaboration. It seems like there's a lot going on behind the scenes to make our C programs run smoothly.
Absolutely. It really is a testament to the ingenuity of all the folks who design these systems and to the power of abstraction in computer science. We can write this relatively high-level code in a language like C, and then all these sophisticated processes translate our instructions into these actions that the computer can actually understand and execute.
Well, we've explored the whole journey of a C program now, from typing out those lines of code in a text editor all the way to it being loaded into memory and ready for the CPU. It's pretty incredible to see how all those pieces fit together.
Yeah, I agree. And it all happens so fast, that we just take it for granted. But understanding this process, it can really give you a deeper appreciation for what's going on under the hood.
And so we've walked through how a C program gets transformed, right? From that pre-processing to compilation to assembly and linking, all leading up to that moment where it's loaded into memory, ready for the CPU to take the reins.
Yeah, it really is kind of amazing when you think about it, all those steps, and it happens so fast. But, once you understand what's going on, it really makes you appreciate all the work that's happening under the hood.
Totally. And speaking of under the hood, we've been calling the CPU the brain of the computer. But how does it actually go about running our program? What's going on down at that level?
Right. Well, that's where we get to the real heart of how a computer works. And it all comes down to something called the fetch, decode, execute cycle. It's It's the fundamental process that drives everything the CPU does.
Okay, that sounds important. Break it down for us. What happens in each of those steps? Fetch, decode, and execute.
All right, so first in the fetch stage, the CPU grabs the next instruction from memory, and it knows where to look because of something called the program counter. That keeps track of where the current instruction is. Think of it like a bookmark in our code. It tells the CPU where to read next.
So the CPU fetches the instruction. Got it. Then what?
All right, so next comes the decode stage. Now the CPU has to analyze that instruction it just fetched. It figures out what operation it needs to perform, like is it addition, subtraction, is it moving some data around, or something else entirely. The CPU also has to figure out what data is involved, so which values from memory need to be loaded and used in the operation.
Okay, so it's kind of like the CPU is reading the instructions, figuring out what it needs to do, and gathering all the ingredients, right?
That's a great way to put it. And then finally, we get to the execute stage. And this is where the CPU actually performs that operation that's specified by the instruction. It might use its arithmetic logic unit, we call that the ALU, to do calculations. Or it might move data between registers, which are like temporary storage spots inside the CPU itself.
So if our program is adding two numbers together, the CPU would have fetched the instructions to load those numbers into the registers, decoded those instructions, and then now, during execute, it's using the ALU to actually do the addition.
Exactly. You got it. And once that operation's done, the results might get stored back into memory, or they might be kept in a register to be used later on. Then the CPU updates the program counter, so it points to the next instruction. And the whole cycle starts over again. Fetch, decode, execute. And this just keeps going and going and going until the program ends.
Wow, that's pretty incredible. It's like this super fast, super precise dance that's happening inside the CPU. Fetching, decoding, executing, all perfectly in sync.
It really is a remarkable feat of engineering, especially when you consider just how many instructions modern CPUs can handle per second. But remember, the CPU is not a lone wolf here. It's working very closely with the operating system, which is managing, all those resources we've been talking about.
Right. The operating system takes care of stuff like displaying text on the screen or reading input from the keyboard. It provides all those services to our program, so we don't have to worry about the nitty-gritty hardware details.
Exactly. It's really a powerful partnership. It lets us write relatively high-level code in languages like C, and then have it all translated down into those precise instructions that the CPU can handle.
Well, we've really explored the whole life cycle of a C program now, from those lines of code you type in your editor, all the way to that incredible dance happening inside the CPU, the fetch, decode, execute cycle. It's amazing how it all comes together.
I agree. It really shows the power of abstraction in computer science, building up these complex systems from simpler building blocks. And it all works so smoothly, we take it for granted most of the time.
So to all of you listening out there, next time you're writing some C code, take a second to appreciate that invisible orchestra that's playing behind the scenes, right? From the preprocessor to the compiler, assembler, the linker, the loader, and finally the CPU. It's an incredible journey that brings your code to life. And understanding how it works can make you a better programmer, a better debugger, and just a more well-rounded tech person overall.
Couldn't have said it better myself. So as you keep learning about C and keep experimenting, remember, there's always more to discover. Keep diving deep.